Hi guys, welcome to topic 7.5. This lesson is going to be over what's called valence shell electron pair repulsion. It sounds very intimidating. It's also known as VSEPR, and you're going to discover here in a little bit that it's really not as bad as the name sounds. And so what we've done so far is looked at the different ways in which electrons can be shared in a covalent bond. And so now we're going to start looking at what these molecules actually represent in our world in terms of a three-dimensional shape, and then what angles they take on. So for this video, you're going to definitely need a periodic table, and then attached in this lesson post, there is also this handout that is the VSEPR table, and you're definitely going to need this here momentarily. Actually, if you want to, after I give you these instructions, what I would highly recommend that you do is if you look at the bottom of your handout, you have this big table that we're going to work through. Go ahead and pause the video and work through the Lewis structures and use this as an opportunity to kind of see how things are going in terms of drawing your Lewis structures, okay? So hopefully you took my advice and paused the video, and you can see here in a moment how you did in terms of coming up with your Lewis structures. So what is VSEPR, or valence shell electron pair repulsion? So we've been drawing a Lewis structure. The only thing we do differently is we show these two electrons here as a bond, the single bond between the hydrogen and the oxygen. So it's just showing a flat molecule of water, and it doesn't give any characteristic to it. So what we actually are going to do is start looking at molecules as being three-dimensional, because they are indeed three-dimensional. They're not just these flat things on a piece of paper. So here is a poor representation, but this is kind of what water looks like. It's a V-shaped molecule, and then it has these lone pairs. So sometimes textbooks can use this representation like this, where they take this Lewis structure and translate it into here, because water is actually a V-shaped molecule. And so what we have is oxygen as the central atom, and they use these bonds here and shaded them the way that they did to kind of tell the viewer that this hydrogen that's shaded in black is coming towards you, and that this hydrogen is going away from you into the page. And there's these lone pairs that are helping cause water to take on this V-shape appearance. And so that's one thing hopefully we can get PhET to work, and you guys can work on a simulation with VSEPR. So again, why do molecules take on a 3D shape instead of being flat? So again, VSEPR is just an acronym for that valence shell electron pair repulsion theory. So again, if you remember back, electrons, we know that they exist in pairs, either through a lone pair or through a bond, and they have a negative charge. And so if you put electrons together, they are not going to want to occupy the same region or three-dimensional space. And so they repel one another. So the idea is molecules take and adjust their shape. So there's different shapes that things can take on, water being a V-shaped molecule. And it's so that the valence electrons can take up basically and have their own region of space. So the idea is, if you think about it kind of 360 degrees, what can that molecule do to give everything equal amount of that 360 degrees to keep those electrons as far apart from one another as possible? So both shared electrons in a single, double, triple bond, and the unshared electrons in those lone pairs on the central and outer electrons, again, are on the outer atoms that are attached to that central atom, are going to repel one another because of that negative charge. So like I said, it's a fancy way of just saying electrons want their own space. So, like I said, I hope you took a second to pause the video to draw out your Lewis structure for methane, or CH4, or carbon tetrahydride for the naming system that we've been taught, because we haven't done organic naming. You have 8 electrons. You should put carbon in the center and have 4 surrounding hydrogens. So this part is not the new part of the lesson. The rest of the table is, however. So what you do next is we have to figure out what shape does carbon tetrahydride take on according to this Lewis structure. So the geometry of the molecule is always based upon your central atom. Okay, so in this case, carbon is our central atom. So you look at what is surrounding it. So surrounding the carbon, we have 1, 2, 3, 4. So we have 4 bond pairs, and there are no lone pairs on that central atom. So from there, and based on that information and the idea that electrons repel, we can determine what shape it's going to take on. So that's where this lovely table comes into place. So here it tells you right here we have the central atom and we have bonds and lone pairs. So we're going to follow this table down until you find that it has 4 and 0, which is just about maybe a third of the way down. So we have 4, 0. The shape is going to be tetrahedral. And then if you follow that over just a hair more, that means 109.5 degrees. So what that means is between these bonds here, between the hydrogen to hydrogen, there's approximately 109.5 degrees. And that's between all of these to, again, divide up a three-dimensional space. And hopefully in my next video, I'll dig out my molecule set and I can build these for you so you can kind of see a little bit more in terms of what I'm talking about, if we can't get the PhET simulation to work. So the next one we have is water. Water also has 8 electrons, but it's not going to have the same shape because our Lewis structure ends up with oxygen as our central atom with 2 lone pairs. So when we go to answer this, we look again based on our central atom. The oxygen has 2 bonded pairs to it and 2 lone pairs. So for our shape, we follow this through. It is 2 and 2. So in this particular handout calls it bent. Sometimes it depends on the publisher and who's making it. These are also sometimes called V-shape. And so this is 104.5 degrees. And so again, when we look at water, we have this oxygen and hydrogen. Again, it's because of these lone pairs that there's that repulsion, and that's what causes these hydrogens to have to come closer in contact with one another because of those lone pairs on the central atom. So ammonia, NH3, or nitrogen trihydride, based on the naming system we have been taught. We also have 8 electrons yet again. We have nitrogen. It should have ended up with a lone pair. Oops. That is an H, not an N. And so when we look at our central atom here, we have 3 bonds, 1 lone pair. Following our chart, we're looking for coordination of 3 to 1. So when we follow that here, we have 3, 1, and we get a name called trigonal pyramidal. So kind of like the name implies, it's basically nitrogen sits up here with its lone pair, and these 3 hydrogens are kind of like the base of a pyramid. Again, one going kind of towards the back, one out to the side, and one coming towards you. So again, it's representing something three-dimensional. So again, when we look at the angle there, we have 107.5 degrees. So from here, things change a little bit. So those ones were pretty easy, and there's just a couple of other rules to follow. So oxygen, when you drew its Lewis structure, it has 12 electrons. So in order for everyone to get a complete octet in this example, you needed to draw a double bond. So again, anytime I set up your notes, there's usually a reason to why I have the examples I do. So bond pairs. I know you're thinking there's 2 bonds, so therefore it has 2 bond pairs. Really what I mean here is bonding regions. And the other thing is this molecule doesn't have a true center. They are a replica of one another or symmetrical. And so we're basically going to talk about one of the oxygens. So we don't count a double or a triple bond as multiple bond regions. This is going to count as one. So again, double and triple, you count as 1, not as 2 or 3. And then on that oxygen, there are 2 lone pairs. So then the rest of it's the same as what we've been doing. We're following our chart looking for 1 and 2, and this is linear. Now, I know some of these, it doesn't really have an angle. Linear, typically, if you think about it, 360 degrees. How can you possibly spread out as much as possible? 180. So we'll just put 180 here for the angle. All right, and I believe just one last, or no, we have 2 more examples. So PCl5 was from our last lesson on Lewis structures. So this one is a scenario where we have an expanded octet. So they all end up on our central atom. And so when we look at our phosphorus, we have 1, 2, 3, 4, 5. So 5 bond pairs, none of which are lone pairs. Following our chart, we just go a little bit about halfway down. We end up at 5, 0, which is called trigonal bipyramidal. And then looking at the handout, we have 2 different degrees going on. And like I said, I'm going to have molecules built when I go through the answer key for this, and I can help explain why we have these 2 different angles. Because again, looking at it on a piece of paper, well, actually, so what it's saying is the angle here is a 90 degree between these chlorines here. And then as we swing around to this part, we have 120 degrees. So again, when I build that, I can show you what a trigonal bipyramidal actually looks like 3-dimensionally. All right, so the last example, again, there's a reason why I have it. So this is when we had to build a symmetrical molecule. Nitrogen starting out in the center, and you have enough electrons to complete each of them with a lone pair. So kind of like the O2, we don't have a true central atom. So again, you pick 1/2 of the molecule. And so we're going to emphasize, and again, it doesn't matter which one you pick because they're each the same. So we have 3 bonds on it and 1 lone pair. So then when we go to our handout, we have 3 and 1, and we get trigonal pyramidal again. And we get 107.5 degrees. All right, so that's your lesson on VSEPR. So it's just looking now at the shape of our Lewis structures. So if you have any questions, need more help, please let me know.